In section 13.2, you're going to take what you learned from section 13.1 about how to determine if a function is increasing or decreasing, to also use that information to identify relative extrema. That's a fancy word for finding a maximum or the minimum of a function. So take some time to read the book, go through the notes. In this video, I'll work examples 3b, 3c, and example 4. So I'm going to go through the last 2 pages of notes with you as we get into this information. So when you're ready, example 3b, we have this function f of x equals 6x to the 2/3 minus 4x. We are looking for relative extrema, or where this function has a maximum value or a minimum value. So the first thing we have to do is find the derivative. So in this case, f prime of x is going to be 6 times 2/3 x to the negative 1/3 minus 4. Multiplying 6 times 2/3, let's see, 3 goes into 6 2 times. That leaves behind 2 times 2, or 4x to the negative 1/3 minus 4. So there's our derivative. Now you can leave it like that, or you can view your derivative some other ways, depending on what makes most sense to you. We could also say the derivative could be written as 4 over x to the 1/3 minus 4, or you could also see it as 4 over the cube root of x minus 4. All 3 of those are equivalent. Probably the easiest one to work with algebraically is going to be this last perspective. Seems to make the most sense to our brains. So find the critical numbers by noting where f prime of x is undefined and by solving f prime of x equals 0. Remember, those are the 2 things we check when we're looking for critical numbers. Where is it undefined, and where is the derivative equal to 0? So if I look at the function, because I have this denominator here, where that denominator is equal to 0 causes my derivative to be undefined. And clearly, when x equals 0, f prime of x is undefined. So x equals 0 is one of our critical numbers. To find any other possible critical numbers, I'm going to set my derivative equal to 0. So I need to solve 0 equals 4 over the cube root of x minus 4. Well, let's add 4 to both sides. And then let's divide both sides by 4. When I divide both sides by 4, I end up with 1 equals 1 over the cube root of x. When we multiply both sides by that denominator, cube root of x, we end up with cube root of x equals 1. Now to finish out, let's raise both sides to the 3rd power, and we end up with our other critical value, x equals 1. So it looks like we have 2 critical numbers. 0, where the derivative is undefined, and 1, where the derivative is equal to 0. So we want to put both of these numbers on a number line. This is going to feel a lot like what we did in section 13.1. So let's make our number line. And let's put our critical numbers on that number line, and don't forget to put them in numerical order. I know that seems like such a simple comment, but how many times have I just stuck my numbers on there and they weren't in numerical order? Now, we need to observe, we've got 3 intervals created, and we need to choose test points in each interval to determine the sign of the derivative on that interval. Now, don't forget, our derivative was 4 over the cube root of x minus 4. Okay, so I'm going to figure out the sign of that expression on each interval. So let's figure out a test point less than 0. I'm going to use test point -1. If I plug -1 in for x, we know the cube root of -1 is -1. So we have 4 divided by -1, which is -4, minus another 4, and we would get some number that's negative, right? Remember, you don't care about the value, you're just looking for the sign. So our derivative is negative on that first interval. Next, we need a test point between 0 and 1. The first one that pops into my mind is 1/2, or 0.5. Whenever I plug this number in for x and calculate, we want to figure out the sign. Now I might need a little help with calculating this one, so I'm going to use my calculator. So there's our stuff from 13.1. Let's clear that up. And we're going to evaluate 4 divided by, now to get the cube root, you press your math button, arrow to number 4. See the cube root there? And press enter. We want 4 divided by the cube root of 0.5, or you can type in 1/2. I'm going to arrow to the right to get out of that radical and subtract 4. And remember, we don't care about the value. We're observing that's a positive number. So back to our sign graph, we can say the derivative is positive on that interval. We've got one more interval to test. We need a test point bigger than 1. I'm going to try to choose something convenient to calculate with, maybe something that's a perfect cube. So the next perfect cube bigger than 1 would be 8. That'll be an easy number to use. But remember, you can choose anything bigger than 1. So if I take 8 and I plug it in for x, we know the cube root of 8 is 2. 4 divided by 2 is 2. And 2 minus 4 is a negative number. So we can tell that the interval 1 to infinity has a negative derivative. So just kind of imagine your graph. We don't know the curvature of the graph, but we can say it's going down on this interval, then it's going to be going up, and then it's going to be going down. Now I can visualize this is going to be a minimum, and that's going to be a maximum. So the function f has a relative maximum at x equals 1. The value of this maximum is, now, I don't want to plug that back into my derivative, because if I plug it back into my derivative, I'm going to find out my derivative is 0. That's where that number came from. So to get the value of my function, I got to go all the way back to the beginning to my original function. And I'm going to plug 1 in for x. Now remembering that 1 to any power is always 1. Ultimately here we have 6 times 1 to the 2/3, which is 6, minus 4 times 1, which is 4. So 6 minus 4 equals 2. So the function value there is 2. Okay, notice we used f, not f prime. So at x equals 1, the maximum value is 2. So the ordered pair 1, 2 will be on the graph of the original function. Okay. Also, f has a relative minimum. See the bottom point here? At x equals 0. This relative minimum is f of 0. Now remember, we got to go all the way back to the original function. When I plug 0 in for x in my original function, I'm going to end up with 0. So the function, looking at our sign chart, is increasing there in the middle. Now reading the leftmost x value to the rightmost x value, it's increasing on 0 to 1. And it's decreasing where it's negative. So I'm looking at this interval from negative infinity to 0. It's decreasing. And it's decreasing on this interval. Leftmost x value there is 1, rightmost x value is infinity. So we can make a pretty good graph if the problem required us to do so. All right, let's move on to example C. We're still looking for relative extreme values. Where's the maximum and where's the minimum? And this time we're going to be dealing with the function f of x equals x cubed times e to the x. But we're using the same procedure. So the first thing we need to do is find the derivative. Now, can you determine which rule is appropriate for finding the derivative here? I'm assuming you said the product rule, right? Because we're dealing with the product of two functions of x. So the product rule says we keep the first function the same, and we multiply by the derivative of the second. That's a hard one, right? Derivative of e to the x is e to the x. Plus the derivative of the first function, that's 3x squared, times the second one, e to the x. So there's our derivative. Now, we know we're about to set this equal to 0 and try to solve for x, and it's always convenient to do that if it's factored. So let's go ahead and factor it right here. Notice the greatest common factor between the two terms there is x squared e to the x. So when we factor that out, that leaves behind x plus 3. Now, when we set our derivative equal to 0, it's factored and ready to go. All we have to do now is set each factor equal to 0. So notice there's 3 factors there, okay? So when I set my first factor, x squared equal to 0, and take the square root of both sides, I get my first critical number, which is x equal to 0. I'm going to take my second factor there, e to the x, and set it equal to 0. Now, there's a problem with this one. E to the x is never equal to 0. So that simply means I'm not going to get any information out of that one. Now, if you're wondering, how did we know that? Don't forget, when we graph e to the x, remember it's always above that x-axis. In fact, there's a horizontal asymptote there. So the function value, the y value, is never equal to 0. So pretty much I can ignore that middle factor. No information from that one. Then finally, when I set my third factor equal to 0, I end up with another critical value, -3. So we have 2 critical values to consider. If this function has a max or a min, it would be only at those 2 possibilities. So let's construct a number line containing these 2 critical numbers. And then we're going to observe the intervals created by the critical numbers. We're going to choose test points and figure out the sign of the derivative. That's just like what we did in the previous section. So on our number line, I've got 2 values, 0 and -3. Now again, be careful. Make sure you put those in numerical order. So -3 has to go on the left. 0 is going to go on the right. Now, because our derivative was factored, I can determine the sign of the derivative by determining the sign of each individual factor. Now, one of these is going to be easy to determine. Remember this e to the x graph that we're looking at? Well, it's always above the x-axis. It's always positive. So I'm not going to think too hard about that factor. I know it's positive no matter what I plug in for x. Also consider x squared. No matter what number I plug in for x, when I square it, it also is always positive. So x plus 3 is the defining factor. I'm going to determine the sign of x plus 3 on all of these intervals using test points. So what is your favorite test point less than -3? Did you say -10? I don't know. Maybe you said -4, right? Anything less than -3 would work. When I plug that test point in for x, I evaluate -10 plus 3. I observe the result is negative. So a positive times a positive times a negative gives me a negative derivative. So we know that it's decreasing on that interval. Let's pick a test point between -3 and 0. I'm guessing your favorite test point is -1. Am I right? -1 plugged into our factor, -1 plus 3 gives me a positive number, and a positive times a positive times a positive is positive. So our derivative is positive on that middle interval. Now, favorite test point bigger than 0. I bet you said 10,000, right? Remember, anything greater than 0 will work. Any test point represents that interval. So if I plug that number into my factor, I see that it's positive, and a positive times a positive times a positive is a positive. Now this is okay. The signs don't have to alternate over every interval. You may have some repeating signs like this. So don't think that you have a problem if that happens. So let's think about the shape of our graph. It would be decreasing, and then it would be increasing, and then it would be increasing again. So I can see that a minimum is formed right there at -3. So the function has a relative minimum at -3, and the function value, remember we got to go all the way back to the original function to find the function value. If you'll recall, the original problem was x cubed e to the x. So f of -3 is -3 to the third power times e to the -3. -3 to the third power is -27. So we get -27 e to the -3. Or you could say -27 over e to the third power. However you want to look at it is fine. It is decreasing on the interval. So looking at our sign graph again, remember we're looking at where the derivative was negative. The leftmost x value here to the rightmost x value. So -infinity to -3. And it's increasing on the interval -3 to 0, union 0 to infinity. So I'm just including both of those two intervals. Okay? Now, on the next page, we're going to be looking at applications. Example 4 deals with revenue, profit, and cost. But we're still considering what happens when we set our derivative equal to 0, when is it positive, when is it negative? Same type of mathematics. So this problem says a small company manufactures and sells bicycles. The production manager has determined that the cost and demand functions for Q, now it says Q has to be greater than or equal to 0. Q is the number of bicycles. We're not going to make a negative number of bicycles, right? So Q is the number of bicycles per week. The cost function is C of Q, and the demand function D of Q. And remember, P is the price per bicycle, okay? So find the maximum weekly revenue. Now, just to kind of give you a heads up, on part A, we're looking at maximum revenue. On part B, we're looking at maximum profit. Get it in your mind, those two things are very different aspects. So as a business calculus student, you need to make sure you know the difference. Revenue is how much money you make from the sale of your product. Profit is what you get after you pay for all of those costs. So let's determine the revenue function. Now, logically, the revenue function is going to be the price of each bicycle times the number of bicycles that I sell. The price is given by our demand function up here. So I'm going to take 90 minus Q and plug it in for P, and that's going to give me my revenue function. Now, let's go ahead and break this up. So officially, our revenue function is 90Q minus Q squared. Now, I want to figure out what's the maximum revenue. So don't worry about the words here. Maximum of a function, we know that means where is the derivative equal to 0. So let's find R prime of Q. R prime of Q is 90 minus 2Q. Now, I want to figure out the critical number. That's the place I'm going to inspect for a maximum or a minimum. And we find that by setting our derivative equal to 0. So we need to solve this little equation for Q. If we add 2Q to both sides and then divide both sides by 2, we're going to end up with Q equals 45. So the critical number is Q equals 45. Now at this point, I don't know if that's a maximum or a minimum. I need to verify that by checking the sign of the derivative on both sides. That's a really important thing to check, because if your boss says maximize revenue and you accidentally minimize revenue, well, you might be fired, right? I would just take a couple of points off your test, but if I'm your boss, I probably wouldn't be so lenient. So let's think about our derivative. Now, if you want to make a sign graph, we know the only one we're checking here is 45. And my derivative was 90 minus 2Q, so that's what I'm plugging my test points into. Let's pick any test point less than 45. How about 10? 90 minus 2 times 10 is a positive number. And then any test point bigger than 45, how about 50? 90 minus 2 times 50, or 90 minus 100, would give me a negative number. So we know our function is increasing and then decreasing. So it looks like we do get a maximum at 45. So this shows that R of Q is increasing up to Q equals 45, and then decreasing. So there is a maximum value at Q equals 45, but we want to find that value. To find that value, we need to go all the way back to our original revenue function, this guy up here, and plug in 45. So we can take 45, plug it into our revenue function. How about we do that with our calculator? So we would have revenue function 90 times Q, which is 45, minus 45 squared. Looks like our maximum revenue is $2,025. So maximum revenue, since it's dollars, I'm going to write the dollar sign there, 2025. So the maximum revenue will be $2,025 and will occur when we make 45 bicycles. Okay, so if we make 45 bicycles and sell them, we will make $2,025 per week. Now, on the next part, we're going to find the maximum weekly profit. Do you think that maximum revenue and maximum profit occur at the same production level? What I mean by that is if I produce 45 bicycles, I know that I'm maximizing revenue, but am I also maximizing profit? It's kind of an interesting question, and the answer might surprise you. So let's find the maximum weekly profit. The calculus part's going to be the same. The logic, the math's going to be the same, but we're going to be using a different function. We need to find the profit function. The profit function, P of Q, is obtained by taking our revenue function, the amount we made from the sale of the bicycles, and subtracting our cost. That might be materials, labor, overhead, that sort of thing. Now, in the previous example, we discovered that revenue was 90Q minus Q squared. And the cost function was given in the original problem at the top of the page. It's 10 plus 5Q plus 1 over 60Q to the third power. Okay, so I need to simplify all this stuff. So I need to distribute this negative and see about combining like terms. So simplifying, the first two terms are going to hang out for a minute while I distribute the negative to get minus 10 minus 5Q minus 1 over 60Q to the third power. Now, to keep it organized, make sure I don't miss anything, I'm going to rearrange it in descending order. So I'm going to start with my highest powered term, which is negative 1 over 60Q to the third power. Got that one. Then I'm going to go for the next highest powered term. That's going to be the minus Q squared. Observe we have a couple of like terms here. 90Q minus 5Q. That gives me plus 85Q. Don't forget about our constant there, negative 10. So we have our profit function. Next, I want to maximize profit. So anytime you want to find a maximum or a minimum, you need a derivative. So let's find the derivative of our profit function. So the first term, we have coefficient negative 1 over 60. The derivative of Q to the third power is 3Q squared. The derivative of the next term is minus 2Q, and derivative of 85Q is 85, and the derivative of minus 10 is 0. If I reduce negative 1 over 60 times 3, I end up with negative 1 over 20 Q squared minus 2Q plus 85. So I need to find the critical numbers. We know to find the critical numbers, we are supposed to set the derivative equal to 0. Now, this one's not a lot of fun to factor for a couple of reasons. Number one, there's a fraction as the leading coefficient. And number two, if you sat down and worked with it for a while, you'd realize it doesn't factor. So what do you do when it doesn't factor? You resort to that quadratic formula. Now, when we plug numbers into the quadratic formula, it might be easier to view this one as a decimal instead of a fraction. So notice that negative 1 divided by 20 has the decimal value negative 0.05. So I'm going to rewrite that as negative 0.05. Okay, so in our quadratic formula, A is negative 0.05, B is negative 2, and C is 85. So our quadratic formula, Q equals negative B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. negative b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully you remembered that formula. Now, let's just plug this into our calculator. I'm going to let my calculator do most of the work here. I am going to be careful with my numerator and denominator. When I plug it in, I'm going to make sure and get a couple of sets of parentheses there so the order of operations turns out right. Okay, so I'm going to start with opening parentheses. I do have a negative 2 there. I know that's going to cancel to a 2, so I'm just going to type that as a 2, plus the square root of b squared. I know negative 2 squared is 4, so I'm going to save some typing and evaluate that one. Minus 4 times a, negative 0.05, times c. Now be careful here. Make sure you use your right arrow key to get out of that radical. Close the numerator, divided by, be careful here, open a set of parentheses for your denominator, and we have 2 times negative 0.05. Close parentheses for the denominator and press enter. So the first Q value we have is approximately negative 65.8. Now, don't forget to think about what we're modeling. Q was the number of bicycles we were producing. We can't produce negative 65.8 bicycles. So essentially, that's extraneous information. It's the correct critical value, but it's not going to be relative to my problem. So I'm going to ignore that one. The first time around, we did the plus from the quadratic formula. The second time around, we'll use the minus. And you can shortcut this. If you'll do second entry on your calculator, and then I'm going to do second left arrow key to go all the way to the left. And I'm just going to edit that first plus to a minus and press enter. We come up with 25.8. That is a reasonable number. So Q equals 25.8. Reasonable because it's positive, but can we make 25.8 bicycles? Not quite, but we can make 26. So let's go ahead and round it up to 26 bicycles. Now at this point, I don't know if that maximizes profit or minimizes profit. So I have to check both sides of 26 from my derivative to make that call. So let's put our critical number 26 on the number line. Our derivative was up here somewhere. That's what I want to evaluate. So I'm thinking negative 0.05 q squared minus 2q plus 85. So I need a test point less than 26. How about 20? And I'm going to need a test point bigger than 26. How about 30? Now, if you plug those into your function and used your calculator, you'd find out it's positive on this side and negative on this side. That's good news. Do you know why? Well, if my function is increasing and then decreasing, that means a maximum profit is possible. So the maximum value occurs when Q equals 26. That is, we're making 26 bicycles. And now I have to figure out what is the maximum profit. Now, I'm not going to plug it into my derivative. I'm going to plug it into my original profit function. And I feel like I need the calculator on this one. So if I take 26 and using my calculator and I plug it in up here, we would end up with the value $1,231.07. Okay, and you can verify that by plugging it into your calculators. Thus, the maximum profit of $1,231.07 occurs when 26 bicycles are produced and, sorry about the typo, sold each week. Now, what was it for maximizing revenue? To maximize revenue, we had to produce 45 bicycles, but to maximize profit, we only need to do 26. This is not the same number. Isn't that interesting? Good thing we looked at maximizing profit. Takes a lot of hard work, a lot of labor, a lot of materials to produce 45 bicycles. It maximizes revenue. But when we subtract our cost, it doesn't pay off. We only need to make 26 bicycles to maximize profit. So find the price the company should charge to realize maximum profit. As shown in part B, 26 bicycles per week should be produced and sold to get the maximum profit of $12.3107 per week. Since the price is given by, now remember the price was up here in the original problem, it's from our demand function, it's determined by 90 minus Q. The Q that we're looking at here is 26 bicycles. So we need to evaluate 90 minus Q, or 90 minus 26, which gives us 64. Thus, the manager should charge $64 per bicycle and produce and sell 26 bicycles to get the maximum profit of $12.3107. Now, I like that price. That's a good price for a bicycle. I hope these videos are helpful. If you get stuck or you have questions, remember you can email me or contact me by phone anytime you need help. So keep working hard, and I will see you in the next video.